we're starting our last unit of the semester, and we're going to start looking at something known as mole calculations. But before we do that, today what we're going to focus on is something known as formula mass and then also percent composition. So formula mass, you're going to see that word. You're going to see many words that all mean the same thing. Formula mass, formula weight, molar mass, molar weight, gram formula weight, molecular mass, molecular weight. All of these things mean exactly the same thing. And what it is, it's the mass of that compound and the mass of it in grams. Well, when we talk about the mass of that compound, how much of that compound? 1 mole of that compound or element or whatever that substance happens to be. So formula mass, molar mass, all of those things mean the same thing. It's the mass in grams of 1 mole of that substance. So of course that brings up the question, what in the world is a mole? So a mole, and you do not have this on your notes, we focus on this really more next lesson, but I just want to bring this up right now, that a mole is what chemists use to indicate an amount, a count. So you can kind of think of it as a count. Just like if you were to go to the store and buy a dozen cookies, you would be buying 12 cookies. If you go and get a ream of paper, you've got 500 sheets of paper. If you get a gross of pencils, you have 144 pencils. So it's just a way of grouping things together. And this makes a lot of sense to us because we're going to be working with atoms and molecules, things that are really, really, really tiny. When we go back to lab, we're not going to be counting those individual particles. We want to work with big groups of those particles. So we work with something known as a mole, and I'll talk about that number next time. But by grouping these numbers together, we get a smaller number to use in practical situations. For example, if you have 288 paper clips, instead of really counting all those out, you can just work with 2 gross of paper clips. That's just kind of a more, I guess, familiar example. Okay, since we're frequently concerned with relative amounts, we can use the mole without being overly concerned about counting each of those tiny little particles, the atoms or the molecules, and converting it. Okay, so again, you do not have this on your notes, but I'm going to sum this up. Maybe you want to write this on your notes, that you could say 1 atom of carbon-12 has a mass of 12 atomic mass units. 1 atom of carbon-12 is equal to 12 AMU. We actually looked at that back in Unit 3 when we talked about where the mass of a proton came from, and we talked about it coming from carbon-12. Well, you have 12 protons in carbon-12. I'm sorry, that's completely incorrect. You have 6 protons in carbon-12 plus 6 neutrons in carbon-12. So you have a total of 12 nuclear particles, and they have 12 atomic mass units for that. So that's a little impractical. We're not going to be working with atoms back in lab. Instead, we'll work with a mole of carbon would be a much easier way to do that. So 1 mole of carbon-12 equals 12 grams. So notice the only 2 things I changed here. I changed atoms to moles, and I changed AMU to grams. So it's much more practical for us to work with a big group of carbon-12 atoms. And we would see that if we worked with if we had a mole of carbon-12, it would have a mass of 12 grams. Anybody figure out where that 12 grams comes from? All the eyes are being directed to the periodic table here. So it's that atomic mass. Everybody's looking at that atomic mass, and you see it's 12.01 grams on the periodic table. What that means is it's that 12.01 grams, and remember that's the average atomic mass, but 12 grams for every 1 mole of carbon-12. And I haven't told you how many, what that count is. That's not important for us today. Just knowing that a mole has a mass of 12 grams. So I can look at my periodic table and I can say, yeah, if I had a mole of potassium, there would be 39.10 grams of potassium in 1 mole of potassium. All right, so then we get to this. This is what is actually on your notes. We want to go through and calculate our formula mass for each of the following. And remember, many different ways to phrase formula mass, but molar mass, just make sure you're familiar with all of those. Okay, first one that we see, sodium chloride. This takes us back to our test that we just had over nomenclature. Sodium chloride, I would look at that and say sodium, Na with a +1. That's a metal. It has a +1 charge. Chloride, Cl with a -1. So that's it. It is electrically neutral right now. That's the only way to write that. I'm going to go through and write all of these really quickly. Next one, arsenic trichloride. This actually happened to be on your test in the opposite direction. It was written that way, arsenic trichloride, AsCl3. So in this case, remember, if you're working in the opposite direction where you're given the formula, because a few people miss this one, you would look at arsenic and see that it's a non-metal. It's over to the right of the zigzag line, meaning you do not think about charges. Instead, you're going to think about prefixes. You've got two nonmetals, so it's arsenic trichloride. Potassium sulfate, K with a +1. Sulfate, SO4 with a -2, so K2SO4. Ammonium phosphate, ammonium, NH4 with a +1. Phosphate, PO4 with a -3, meaning we need 3 ammoniums. So that's how we write those formulas, the only way to write those formulas. If we want to calculate the mass of that compound, let me just start with my sodium chloride. I know that the mass of 1 mole of sodium is 22.99 grams per mole, right? We look at our periodic table for that. So all we're going to do in this case is we're going to write down those individual elements that we find in that compound. I'm going to write down how many atoms I have of each of those elements. I've got 1 of sodium, I've got 1 of chlorine. I look on my periodic table. I multiply that number times the mass, 22.99. Remember our rule of thumb that we talked about when we did average atomic mass? The periodic tables that you guys will be working with in class are rounded to 2 past the decimal. So just stick with what you have on your periodic table in front of you. Work with 2 past the decimal, the hundredths place. Okay, so our sodium is 22.99. Our chlorine, we look and see 35.45. So we found that from our periodic table. In order to figure out the formula mass for the entire compound, you just add that up. And I believe it's 58.44 grams per mole. Do not forget the units. We're looking at 58.44 grams for every 1 mole of that compound. Okay, I'm going to do one more of these and then that's it. I don't think we need to go through all of these. If we look at potassium sulfate, we've got our potassium, sulfur, and oxygen. You go through and you count your number of atoms. You've got 2 potassium, 1 sulfur, 4 oxygens. We said that potassium has a mass of 39.10. Sulfur has a mass of 32.06, and oxygen is 16. Notice I have to do a little bit more math here now because I have more than 1 atom of each. So I go through, and I'm sure everybody is plugging this into their calculators. We go through, and I do not have this in front of me. 39.10, what is that? Someone plug that in. 78.2. Okay, and here we've got 32.06 and 64. So then we just add it all up, and we get, someone might want to double check me, but 174.26, and again, that's going to be in grams per mole. All right, so that's really all there is to formula mass, but hopefully now you're looking at this and saying, aha, I see why it's so incredibly important that I know my formulas. I know how to write these the formulas for these compounds, because otherwise you would get your mass incorrect. Okay, that's all we're going to do on these. We're going to go ahead and continue. And we're going to look at something known as percent composition. Again, I don't know if you have all of this on your paper, but really all we're going to do is try and figure out the percent of each of the elements within a compound. So when percent composition is asked, it means for everything, each element that is in that compound. So this is when we have to drag this back out of our heads. We know this formula. You guys have used this before. What's the generic formula for percent? Part over whole. There we go. Part divided by whole. And then, of course, to get it to percent form, you actually multiply it times that 100. So that's all we're going to be doing. So our first example, it says, if there are 95 grams of barium and 26.3 grams of fluorine in a compound, and you have to assume that's all that's in that compound, just those two things, what is the percent composition? So I'm going to start with my barium, and I'm going to say I have 95 grams of my barium. That's my part. What do I put down in the denominator? What do you want to do? Okay, good. So we add them together. So you could just add them together and plug that number in, or you could do show it like this if you wanted. I just want to make sure that everybody knows that we're adding those two things together. And then, of course, we're going to multiply times our 100%, and we get 78.3% barium. Now, what is pretty important is make sure you write that it's for the barium that we just did that. In your answer, we should see what type of compound or what type of element that is for. Also, you know, we've got 3 sig figs in our given, so let's go ahead and round our answer to 3 sig figs. For the other element, which is fluorine, a couple different ways you can do this. What's the easiest? Subtract it. So you've got your 100 minus your 78.3 is going to give you 21.7% fluorine. And again, making sure that you identify what element you're referring to. Okay, it's just that easy. Next one is very similar. So here it tells us we have 225 grams of a compound. So hopefully you can look at that and say, yeah, that's the whole thing right there. And it's known to contain only phosphorus and oxygen. And we have 114.3 grams of oxygen. What's the percent composition of each of those elements in the compound? So I'm going to start with my phosphorus. And my part is going to be, actually I'm not going to start with my phosphorus. I read through here and it says we have 114.3 grams of oxygen. So I'm going to start with my oxygen. 114.3 grams of oxygen, there's the part, divided by the whole entire thing, which is that 225 grams of your total. So we go through our math and get 50.8% oxygen. And again, I'm going to stick with the idea that here my lowest number of sig figs is 3. I know I have 4 in the other number, but I have 3 sig figs right there. So that's part of it. The last little bit is to figure out your phosphorus. So you're just going to say 100 minus your 50.8 gives you 49.2% phosphorus. Okay, I think people are thinking this is easy. Hopefully everyone feels that way. All right, first 2 examples. Now we move on to something that we saw up at the very top of our paper. Here it says, calculate the percent composition of ammonium phosphate. Again, if it says percent composition, that means for each and every element within that compound, but it doesn't give us any numbers to work with. This is where we have to go back to our formula mass. So the first thing we need to know is that ammonium phosphate, NH4 with a +1, PO4 with a -3, that's how we write that. So now we can go through and identify the number of atoms of each of those elements. So I know I've got some nitrogen, hydrogen, phosphorus, and oxygen. All right, how many atoms do you have of nitrogen? 3. What about hydrogen? 12, phosphorus 1, and oxygen 4. All right, so now you just have your periodic table in front of you and you say the mass of nitrogen is 14.01, hydrogen 1.01, phosphorus 30.97, and oxygen is 16. So then you go through and do your math, and we come up with 42.03, 12.12, 30.97, and 64. And by the way, on this, I would not just throw this all into your calculator. I would write this out because you're going to see that you're going to be using all the pieces and parts of this in the calculation. So you're really going to need to have it in front of you. So don't just throw this into your calculator. Show your work. Okay, when we add this up, we get 149.12. And that's going to be, what units do I need to do here? Grams per mole. Good. So just really get into the habit of writing that down because that's going to help as the units go by in chemistry. So 149.12 grams per mole, but the question is, what is the percent composition of each of those elements within that compound? So in order to figure out nitrogen, what's the part that I have that's nitrogen? What number would I use? Right, 42.03. What do I do with that? Divide it. All right, so I'm just going to continue showing it across like this. So my 42, I just want to make sure everybody understands. 42.03 grams is the part that's nitrogen. 149.12 is the total of my whole compound. And then, of course, I'm going to have to take that and multiply that times 100 to be able to get an answer. So in each of these cases, I am just going to divide by that total mass. In other words, my formula mass. All right, and we get 28.2% that is nitrogen. We get 8.13% that is hydrogen. 20.8% phosphorus, and 42.9% oxygen. So the question was, calculate the percent composition of this compound. You go through, you figure out your formula mass, and then break it down to each and every one of those little individual elements. Now, something worth noting, that if I were to look at this formula right here, I look at that and say, wow, I've got 12 hydrogens. That's the most out of any of these guys, right? To have 12 of those, that's a lot. But when you come over here, what do you notice about your percentage? It's the smallest. So what accounts for that? Why is it such a small percentage? Mass. It has such a small mass. So that's what this is taking into account, both your percent abundance and the mass of these elements. Okay, so that's our third example, last example that we have. Here it's just a little bit different. It says calculate the mass of iron in 150 grams of iron 3 phosphate. Iron 3 phosphate. Iron 3, Fe with a +3. Phosphate, PO4 with a -3. That is electrically neutral right there. So that's how you write it. So when you go through, we're still going to have to do that same procedure and go through and calculate our molar mass, formula mass. We've got 1 atom of iron, 1 of phosphorus, 4 of oxygen. Iron has a mass of 55.85 grams per mole. Phosphorus is 30.97, and oxygen is 16. Do a little math. And we see that the total mass of this compound is 150.82 grams per mole. Okay. I might even pause this for a second and let people think about what needs to be done next. So what you should be thinking about at home is if you have this information, you know the part that's iron, you know the total amount, you also know the total amount that you start with. I'm going to pause and let people here tell me what we need to do. Okay, got some great answers. The first answer was to go ahead and calculate the percent of your iron, which we know it's part, here's your part, divided by your whole times 100, but let's keep it decimalized, and you take that and you multiply it times your original amount. That's exactly what we're going to do. I'm going to set it up in dimensional analysis though. I'm going to say that we're starting with 150 grams of iron 3 phosphate. So in other words, I just wrote this down. Well, I don't want it in grams of iron 3 phosphate. I want it in just grams of iron. So by setting up with dimensional analysis, I am doing the exact same thing. I'm taking my percent iron times my original mass. So my percent iron, remember, is just that 55.85. It's that part that's iron divided by the whole entire thing, 150.82 grams. I know this is a little bit confusing because these numbers are so close and I keep meaning to change that and I keep forgetting to. But so that's all you're doing. Essentially, you're taking that percentage, multiplying it times your original amount. Or you can think about it as setting up in dimensional analysis where your units do cancel. All right, so when we do that, anybody plug that in? What'd you get? There we go. 55.5 grams of just your iron. Okay, that is it. You guys are ready for the holidays. You can 5 little questions there for homework, and that is all.